Pronto. So, okay, good afternoon. Before we start, just a couple of instructions for the barbecue tonight. Thanks to the suggestion of Pierre Pico, here is a very good map. And, well, the Bovinos is right here. This is Rebouças, Main Street. Here is Brazil Avenue. And one side is Brazil, they call, other Henrique Schaumann. And this is the biggest McDonald's of South America, I guess. So it's not, we are not proud of this, but in any case, we have this. And okay, so the let's say the good points to ask information if you are lost is which is the Avenida Brasil, the biggest McDonald's of the world, not the world, but and here is the Oscar Freire yellow line metro station. So if you go by metro, you can it is more or less like here, and you go is a walk distance. You can arrive there. So by metro is better to stop in the Oscar Freire yellow line station. So you just cross, and the Bovinos is like here. I made the reservation for 7 p.m. So we will arrive there, and if you get late, maybe we start 8 before you. So don't be mad, but it's like that more or less. And I think it's okay. For those that don't want to go by metro, we can help to get, maybe you can just get a Uber from here and go directly, but it's really easy if you are achieve Oscar Freire Metro Yellow Station, you can just walk until there. Okay, so now will be the defense of João Maia. He will speak about phase relation using models, the semi-infinite with decay field and long-range random field. I am the advisor, but I will let Luis Renato be the president of the committee. So.
Okay, so we start the presentation by João. I believe we'll have up to 1 hour, 50 minutes. Yeah. Okay, yeah. All right, so please, you can start.
Hello, and now I'm going to present the key results of my PhD thesis. Let me start with an overview of what we're going to do today. So for starts, I'm going to introduce the semi-infinite Ising model, and I'm going to present a result we have when we add a sort of decaying field for this model. Then I'm going to jump to the long-range random field Ising model. I'm just going to present the model. And then I'm going to present this Ding-Zhuang approach. It's a new approach for proving phase transition when you have this kind of, when you have some kind of random field. And at last, I'm going to do some probability estimates that are needed so their proof works for our case. And so for the semi-infinite model, here you have basically a lot of things in common with the usual Ising model. The difference being the lattice. Now we do not take ZD, we take ZD minus 1 times the natural. So you're basically cutting the lattice in half. One important part of this lattice is the wall. That is just the first layer of this new lattice. The configurations are the same. You just take +1 and -1 to the lattice. So in every point you put +1 or -1. And when you put this lambda here, lambda being a finite subset, this is just a restriction of configurations to this lambda. The second important parameter of this model is this wall influence that a priori can be any real number, but we're going to choose it to be positive throughout the paper because otherwise you just repeat everything by spin flip. As in the Ising model, you can consider an external field. Again, can be anything. And the Hamiltonian of this model is the following. So the interaction is constant and is only nearest neighbor. So this This symbol here means that they are actually neighbors. The L1 distance is 1. The external field acts in the same way, so in each side of lambda you put an external field. And the wall parameter comes on this last term here, where you just consider t is lambda, but it only acts on spins that are on the wall, you see. So essentially what's happening here is that you have an extra external field that only acts on the first layer. And again, J is always positive because we want to work on ferromagnetic systems. And here you define as usual the configurations with a boundary condition. There are configurations that met this eta boundary condition outside of the box. So for an example, this is the configurations with minus boundary conditions are like this. So again, you see here, we are cutting the lattice in half, and this first layer is the wall, you see. And outside of this box, we put minus. And you define Gibbs measures as you usually do. So you take the probability of a sigma is just you need to first match the boundary condition, then it's just exponential of the Hamiltonian and a normalizing factor, the partition function. And the Gibbs measure are defined just the same. So we just take the closure of the convex hull of the weak star limits. The same is you just changing the lattice. And this model was extensively studied in these 2 papers by Froelich and Pfister. There are like a wide range of results in here regarding decay of correlations. There's all sorts of phase transition here, all sorts of different interactions. And we are going to focus on only one part of the second paper, that is the so-called wetting transition. So what is this transition? Let's first assume there is no external field, right? So the external field is always 0, and you take this beta critical, the same inverse temperature of the Ising model. And what happens is the following: for beta is smaller than the critical one, there is only one Gibbs measure, because essentially you run this Gibbs model and the Ising model, and there is no phase transition there. The same things happens here. But when you go lower than the critical temperature, then they prove the existence of a critical value, this lambda critical, that satisfies this following thing. So when lambda is strictly smaller than this critical one, there is phase transition. So the mu and the minus, mu plus and minus are different. Macroscopically, this means that when you look at the system, the wall, let's say here you have minus boundary condition. So the black spins are positive and the white spots are negative. And what happens is that the negative phase always touches the wall, you see? So it is always touching the wall. And this translates into having multiple spin systems. But when you take a lambda that is strictly larger than this critical one, then there is uniqueness. And macroscopically, you see a picture like this. So the plus phase, the minus phase never touches the boundary condition, you see? So there is a repulsion, an active repulsion here on the wall. Now, changing a little bit the subject, there is this paper by Bissacco, Cassandro, Celeste, Presutti, where they consider this decaying field. It is a field that decays basically as you go away from 0. So this here is just the size of the site, right? The distance from 0, and you take this delta parameter. So at 0 is just this x star, this h star. H star is a fixed constant, and the field decays. And what we showed is that when delta is bigger than 1, there is phase transition. And for delta smaller than 1, there is uniqueness, but at low temperatures. Sufficiently low temperatures. And when delta is equal to 1 in the critical value, again, there is also, I think here is, incorrect. There is phase transition again, but you need to this is not unique. This phase transition, but you need to assume this H star is small, right? So it does not work for any H star a priori. This result was completed short time later by Cioletti and Villa, where they were able to give a graphical representation for this Ising model with decaying fields. They basically showed that when you do the random cluster for this model, it also satisfies FKG inequality, and with this you can actually remove this low temperature assumption. So they just remove the low temperature assumption and they get uniqueness for all temperatures. Yes. So what we thought to do was to present a notion of decaying field for this semi-infinite model. And what we did is we considered this external field here. That again, this lambda is the same parameter of this wall parameter, but it decays as it goes away from the wall. So it only looks at the distance from the spin to the wall. This d here is just the last coordinate of the site. And again, you have this delta parameter. So here's an example. Here, like we took delta equals 2, and this is how it decays. And this here represents the influence of this external field in our lattice. So in the first layer, you have the same external field, you have the same wall parameter, but this thing decays as it goes away from the wall. But it's constant in every layer. And what we actually was able to prove was that for any dimensions, we take this JC, the critical value of the Ising model. Here we are fixing the temperature as 1 because, as you saw before, this has nothing to do. That has very few to do with the temperature, as long as it's below the critical in the Ising model. The phase transition is regards the lambda parameter. So what we were able to show is that there is again a critical value that dictates phase transition. So for now it depends on J and on delta, but for lambda is smaller than the critical one, there is phase transition, and when the delta is smaller than this critical, is larger than the critical, then there is uniqueness. And we were also able to show that when delta is bigger than 1, and again the J is larger than the critical, then this critical value is strictly positive, therefore there is uniqueness, there is phase transition for small lambda. And when delta is smaller than 1, then this critical value is just 0. So there is always uniqueness. And this is our result for the semi-infinite model. Now let's go to the long-range random field Ising model. Again, the setting is basically the same as the Ising model, so we are in ZD. The configurations are just put -1 or +1 in the lattice. The big difference now is that we are considering long-range interactions, so everybody interacts, and the decay of the interaction goes as the distance to this alpha parameter, alpha being larger than d. This is just the model condition. And the important part is actually that we are considering an external field that is random. So the external field are IID Gaussians. And this epsilon parameter is a positive one. It basically dictates the variance of this external field, right? Since the external field is epsilon times this Gaussian. Well, this is the model. What happens when we are treating this model is that, like, the Hamiltonian or the Gibbs measures are now random variables, right? They depend on the external field. So it might be you may think it's tricky to define Gibbs measures and as you did before, but there's something we don't need to worry about because these weak star limits of the plus and of the minus boundary condition, they exist P almost surely. P almost surely, I mean the distribution of the external field, right? When I use this P is regarding the distribution of the external field. So these limits they exist P almost surely. So we can treat phase transition as these two states are different. and uniqueness otherwise, when these two states are equal almost surely. And the question is now if this external field actually beats the boundary influence, right? Because this external field is trying to disrupt phase transition, because phase transition in the Ising model is essentially you put plus boundary condition, you are forcing the spins to be on average always positive. And when you do the minus, the same thing, but on average they are negative. And the external field tries to beat that and tries to uh, get some sort of a random configuration that independent configuration of the spin. And okay, so what results we have for the short range? So for the short range, you have this paper by Brickman Copiani that they showed phase transition for dimensions bigger than 3, as long as, again, you have to take a small variance. So you take a small variance, you have phase transition. And Eisenman Wern, they proved that in dimension 1 and 2 there is uniqueness. So no matter the temperature, there is always uniqueness. Let me make a historical remark here. This is actually a very interesting case of when the statistical mechanics was important, because in physics they had this debate for a long time if in 3 dimensions you would have uniqueness or phase transition. There are like basically 2 competing arguments, one by Paris and Sorlas, yes, and another by Inhima. And Inhima actually predicted that should be phase transition and 3 dimensions, and he was actually correct. And okay, but more recently, they have this paper by Ding and Zhuang. They get the same result as Brickman-Copiani here. In Brickman-Copiani, there's okay a small difference that Brickman-Copiani only need Gaussian control on the tail of the external field, and here in this Ding and Zhuang paper, you actually need it to be Gaussian. A priori, you can be a little bit more flexible than that. And but the advantage of this proof is that it's much shorter. I think the proof is like 3 pages long, so it's a much shorter proof than by the proof by Brickman-Copiani, and does not use renormalization group. A little time after that, again, Ding and his group, Liu and Xia, both their students at the time, they could prove that the phase transition on the long range on the random field Ising model preserves, in a sense, the critical temperature of the Ising. So if you take this beta critical as the critical inverse temperature of the Ising, for larger beta, you can take a small enough variance, depending on the temperature, of course, but there you still have phase transition. So you can reach up to the critical temperature of the Ising model. For long-range systems, we have in the same paper of Eisenman and Wern, they showed that in dimensions 1 and 2, there is uniqueness when alpha is bigger than 3D over 2. And the only result I know for phase transition is by Cassandro, Orlando, and Pico, where they showed that for this region of alpha, you have phase transition. You just need to assume that the first coordinate is large. Okay, so our result is the following. You take, again, we are in dimensions larger or equal than 3. We get the whole region of the parameter, so alpha bigger than 3, bigger than D. And there's these critical values, not necessarily the same temperature of uniqueness, right? But the point is, for large enough beta and small enough variance, then we have phase transition. The plus and minus states are distinct, almost surely. In our argument, basically, we take the Ding-Zhuang proof, and we have to make some adaptations, because basically our contour system is much different. And we use the contour argument by Afonso Bissacou and Doiranda. We use a lot of estimates from here, again with some generalization. So what is this new approach by Jing and Zhuang? So what is their actual method? You first of all, you consider this joint space. So you are consider jointly the configurations in the external field. Here A is a cylinder and B is a Borel set. Well, the generality you need. And you integrate over the external field, and you take the Gibbs measure. Here you integrate the Gibbs measure on this external field. Right? This Q distribution has this density function, so this term here is just the density of the Gaussian, right? And here you just have the Gibbs measure. And you consider this transformation, that is the transformation that flip things. It can be either the configuration, the external field, but you take this here. So if you take a finite A on ZD, this tau A is just the following. You take, let's say, a configuration here, and you flip everything that is in A, and you do not do anything otherwise. And the key idea of the proof is this simple calculation here, that if you take this density function and you compare it, you take a configuration here and an external field, and you compare it when you flip the configuration in A, and you do the same flips in the external field. When you do something like this, you get a term like this. So you have exponential, and here you have the difference of the Hamiltonians with the flipped configuration and with the original one. But the key difference is that now T0 here means that there is no external field. So you get a difference of Hamiltonians as there was no external field. And the dependence of the external field comes in this quotient of partition functions. So essentially when you do this, you are decoupling the influence of the external field with the influence of the Hamiltonian, of the actual Gibbs measure. It's not 100% like this, because in this partition function you still can see the model, right? But this remaining term here has a very important property, that is this one. So let's call delta A 1 over the critical 1 over beta logarithm of that quotient. So if you take this delta function, Dink and Zhuang proved that the decay of this thing, if you put a lambda here, the tail of this thing behaves like this. So lambda square, and you have to divide by size of A, how many spins there, how many sides there are in A, and the difference behaves. The difference have the tail of the symmetric difference. Essentially, what this lemma is saying, intuitively at least, is that this error function now, this delta A, it behaves like the sum of the external field on A. So you see, you're basically not at every point, but the tail of this error is basically the tail of the term that appears in the Hamiltonian, but you just kill the dependence of the configuration, because in the Hamiltonian there is sigma x multiplying here. And okay, so you have this decay that is some sort that is good enough, and the argument of Ding-1 basically follows some steps. You have to define some bad event. Let's not think of this bad event for now, but let's go one step further. So the idea is you want to do Pile's argument on this joint measure, right? So you have to choose this bad event in a way that you're going to split it in the good event and plus the probability of this bad event occurring. And you have to define this event in a way that in here, when you are restricted to the good event, you can do Pile's argument as usual, as there was no external field. And then you just control the probability of the bad event. So for example, let's think on the short range contours. You take usual Pile's contours. then what should be the bad event? The bad event is this error function. So right, when you're gonna flip a contour, the A you need to choose is the interior of a contour. So you flip everybody in the interior of a contour, you're gonna have this error. And the bad event is that for some contour, this error is just larger than, I don't know, some constant times the size of the contour divided by 2. So this term here is just the price of erasing a contour, and you just say that the error is larger than half of it. Of course, in the good event, all the error is not gonna be, it's gonna be less than half of the cost of erasing a contour, and you can do Parell's argument. And here you have to control the probability of the bad event. Again, in the short range case, all the interiors are connected, and Fisher, Froelich, Spencer, they proved that this probability here has decay exponential of minus constants over variance squared. And here we're looking at connected subsets that contain 0, right? So you take the error and divide by the boundary. And actually, this is the hard part for us to do, because as you can probably imagine, we're gonna use that contour presented by Lucas and by Kelvin yesterday and the day before, and they are usually not connected. So we need to basically do the same thing here, but we're gonna change the restriction of connected. We're gonna remove it, and we're gonna put something different there, but we're gonna still have the same decay. So here I'm going to present the contours again. So as you've seen this before, allow me to go a little bit quick in this part. So okay, our contours are going to be incorrect points, right? So points that have one sign and one of the neighbors have a different sign. So for example, take this configuration. Let me find one here. So for example, this plus is incorrect, right? Because they have a different neighbor. And let me find here. This plus is correct because all his neighbors are also plus. So the boundary of this configuration will be like this. These are all the incorrect points. And again, to define our partition, we need this notion of volume. The formal definition is like this. You take the unbounded connected component of the complementary. This lambda is finite, so this is always well defined. And you take the volume as the complementary of this region, and the interior as the volume minus the original set. Might be a little bit complicated, but with pictures is always better. So, for example, this lambda here, the gray region is lambda, so the interiors are this white region, and this white region, and the volume we just fill everything. This is the volume. And now when we use for the construction of contours this notion of MA partition, and we ask two things. Basically, we ask that it is actually a partition. So when you take an A and you divide it into subsets, the union is everything, and they are disjoint. So you are actually it's actually a partition, and you have this condition on the distance that it depends only on the volume. Depends on the volume. And again, we are gonna always assume. First of all, when I put the partition of configuration, I mean the partition of the incorrect points. And we are always going to assume that is the finest one, which again is well defined. You can construct the finest one. Given two partitions, you can construct the finest one taking intersection. And a priori, you can take any values of M and A. We're just going to fix this one because it's the one that works for our computations. As you saw in Lucas' presentation, we can construct an MA partition. Given an R, there is a construction dependent on this R that will give us probably a non-trivial one. And the idea, you use that mood-scale argument and you give a criterion for removing things at each given step. Again, I'm not going to present this here because you saw it in Lucas' presentation. So, okay, what are our contours then? Our contours are pairs, again, given by this lambda bar, this gamma bar, and this label of the contour. Here, again, gamma bar, you just take the incorrect points. You partition them using the MA partition, and you take one of these components. And the label is used to recuperate, in some sense, the configuration. Why? Because, for example, this is an example of our contours, right? And what happens is that different from the usual Pios argument, our contours have holes, and inside these holes you can have different signs. So, for example, this thin barrier here means that everybody in here is negative, right? And this thick border here means it's positive, and even here is negative again. So we need to recuperate which signs we had in each boundary so we can properly recuperate the contours. And this label function actually writes down the signs, and using that we can split the interior of the contour in the plus and minus interior. Basically the plus interior are the interiors with plus size, and the minus is the same with the minus size. Again, one example, you take our original contour, so this is the minus interior, and this here is also the minus interior, but this here is the plus interior. And again, the total interior is just the union of the plus and the minus, and the volume of the contour is the support together with the interior. Yes. So now, as we said, you need to use Dingen's one approach. You need to be able to do Pios argument, right? So here I'm going to present the ingredients you need to use Pios argument. So define the support plus or minus as the points in the support that are positive or negative. The operation that erases a contour is this one. You flip everything. This operation that erases a contour can be seen as that operation that flips stuff. So what you're going to flip? You're going to flip everything that is in the interior minus, and you're also going to flip everything that is in the support, but that is minus. So you keep plus spins untouched. And what we can actually show for these contours is that the price of erasing a contour on the Hamiltonian is just the size of the contour, which is the first ingredient of a Pios argument. And we can show that if we take this zero as all the contours, here with plus boundary condition, you have the usual externality property, but the important thing is zero is in this volume, so we take contours surrounding zero with size n. And this last property here is just saying that it's another way of saying this gamma is a contour, because we are essentially saying we cannot partition this region in a finer region, right? That's it. You cannot take a contour and partition it in different two contours. So when you take this to zero, we have an exponential bound. It's an exponential of a constant n, right? And these are the two ingredients you need to make a Pios argument. And therefore, if we define the bad event of something like this, we can do Pios argument on these events here. And again, our bad event is gonna be the region we need to flip. Let me notice that we do not flip only the interior minus, we flip also the support, right? But you don't need to actually do that. We need to do a small modification actually of Jenkins one approach. So we're gonna flip only on the interior minus, because things becomes much more simpler. And the bad event is again that the cost, this error function is larger than size of the contour over 4. And the difficult part of our argument is to prove this proposition here, that we can actually bound this probability of the bad event by something of exponential constant variance squared. Okay, as long as the variance again is small. And to prove this result, we use the coarse grain introduced by Fisher-Froelich-Spencer, right, for the short range case. But you need to use some improvements of the entropy bounds presented in Lucas' curva em 2 random. So now let me show you how we do these probability estimates. And as you're gonna see, I'm not gonna give all the details of the proof because I don't think we'll have enough time. I'm just gonna give the main ideas, and I'm gonna skip a lot of technicalities here. So how does the proof work? The proof uses these Dudley entropy bounds. Again, I'm not gonna present here because it's not technically so important. It's actually not necessary because, as you see in Fisher, Froelich, Spencer paper, they do not use this entropy bound. They do the proof on their own without using this. I choose this approach basically because I think it gives a lot of more, maybe can give us a lot more tools to deal with this kind of problem. And actually the connection of their proof with Dudley's entropy bound is in Jing's and Matthew Wirth paper on a two-dimensional Random Field Ising Model. So again, I'm not gonna say explicitly what this bound is, but basically we need 2 ingredients. So what is these ingredients? First, you take a contour, any contour, and at every step L natural, you need to approximate the interior by a region, this let's call a BL region, in a way that you can control the error. So you can control actually how many sites you are making a mistake, right? And hopefully you can get a bound of NLN, something that only depends on which step you are and on the size of the contour, that is this N. And after that, you need to control this BLC0. That is basically all regions on ZD that are actually an approximation of some contour, right? And again, the bound of N, L, and N. And the thing is, the Dudley's bound yields something like this. So you can bound the expected value of the supremum by, you just sum over L, positive L, and you multiply N and M, and you take the square root. And hopefully, we can get bounds that will satisfy this, right? Will be constant size of the contour. And you see here you can see there's clearly a trade-off, right? Because the thing is, let's say you want to take very good approximations there, so you don't want to make a lot of mistakes here. This will make this value here increase, right? Because as you are getting better approximations, you also get more regions. So if you try to reduce this, you're gonna increase this bound. So you get a trade-off there. And okay, so now let me see how we do this, both the approximation and the control. So for the approximations, we took the cubes, these CRL cubes. If you remember, these are the same cubes used to construct the contours. So there are cubes like this. So for example, this large cube is the C3, right? So here I'm thinking R equal 2. So you have eight sides here. And these large cubes is equally split in C2 cubes. So here, for example, this cube here is the C20 cube. Okay. And what's going to be the approximation? The approximation will be the region covered by this collection of cubes. These cubes here are called admissible cubes, and are the cubes that have more than half of the cube are inside the interior. So again, pictures help. So for example, take this contour, right? The contour have interiors, have labels, and so on and so forth. But we are actually only trying to approximate the interior, so only the minus interior matter. You see, here we had another interior, right? But the plus interior, but it just gets erased because we're not. It's not relevant for us. And okay, you have this interior, and you approximate it in this form. So this hashed area is the original interior, and we approximate it by these cubes. So this here stays scale, these two wires stay scale. So in each one of these cubes, you have more than half of it inside the interior, and not on these cubes because they do not have a large interior here. And again, we need to control the error, right? We need to control either these hashed regions that are not covered, or these covered regions, for example, here that are not hashed. And we can actually prove that the error we make is something like size of the contour times the scale, right? Up to this point, we are following Fisher, Froelich, Spencer very closely. These admissibility is the same. This bound here is the same. We just had to redo all the proofs in very good detail because we're exchanging connected subsets for basically something that is not connected at all. So just to make sure everything worked, but it does work. Bounding this BLC0N, bounding the number of admissible regions therapeutic, this is actually much different. Because in here, basically, the connectivity of the contours is a key part of the argument. Let me maybe briefly say why. Because again, we are trying to approximate this region, right? And what they use is that, okay, here you may have several connected components, right, of our approximation. Our approximation is the gray part, right? So you may have different connected components, but as the contours are connected, you can choose a cube here, and a cube here, and a cube here, in a way that they are surrounded by the contour. So as they are surrounded by the contour, you get an estimation of the minimal, you take a minimal path that starts from 0 and touches every one of the components. You take the minimal path and you can bound the minimal path by constant size of the contour because they are enclosed by the contour. And this is obviously not the case anymore for contours. Even that the distance between two connected parts, let's say, the distance between these two parts can be huge, can be something like size of the contour to a large constant. So the same approach do not actually hold at all. But what do we do? First, we notice that this region, it is approximated, is determined by the interior boundary of the collection of cubes. So these cubes are basically the admissible cubes that have a neighbor. This should be a C prime, right? So, but they have a neighbor that shares a face with the cube. Again, pictures are better. So here is our original region, right? The green region, and all these dashed cubes here are the cubes in the boundary here. So all cubes here are in the boundary. They are admissible, and some of their neighbors are not. Again, the gray region is not uniquely determined by these cubes, but it is up to a constant. So it is a good enough. It is sufficient to count how many of this collection of cubes appear. So, and basically why we do this, because again, by Fisher, Froelich, and Spencer, we have a bound on the number of cubes that are in this boundary. The number of cubes in this boundary is at most size of the contour divided by scale to the d minus 1. And this allows to get good estimations for the region. Another ingredient we need, another property of this collection of cubes we need, is that if you take an large L, larger than the small L, then every here in this boundary, it's next to a cube on this C R, L, gamma. This is just the covering of the support. So you cover the support with large cubes, and every small cube may be inside of this cube, or if it's not inside, this next one. So here's an example. So again, if you remember, this is our contours. I did not put labels here because they're not relevant. So these are contours, and we cover it by large cubes. So these the dark lines are the large scale, the 2RL scale, and the dotted region are the small scale. So you cover the contours with these large cubes, and all the admissible cubes in the boundary are either inside one of these contours. In this example, all of them are inside, but something like this might happen. You might happen like you have a small cube here in the boundary of the admissible cubes, and it is not covered by a cube in the covering of the contour, but it is next to one. So it is next to a large cube that, I don't know, let's say this here is part of the support. This here is part of the support. So this might happen. Okay. And therefore, we can bound the number of regions by up here. We just sum over all coverings of the contour. You just take all of the coverings, and you choose the number of cubes. Like as I said, you can have at most this quantity of cubes in the boundary, right? So we choose this quantity of cubes over all the possible choices of small cubes in the large covering. Here, these two are the L minus L. This is just, if you take one large cube, this is how many small cubes there are inside these large cubes. And as you can choose each cube in the covering, you have this side of the covering, right? The last two things we need is that we can actually control how many cubes you need to cover a contour by a construction. We get something that is like size of the contour over an exponential term. Let me maybe make a brief comment here. I think in the version we got from the thesis, there was two different bounds on this. There was this exponential bound, and there was also a polynomial bound. You take this by just L to a large constant. And in the most recent version, we can actually erase the second case, so we can get an exponential bound for every contour, right? There was this dependency of which step the contour was removed, and we could simplify this and get this exponential bound on everything. Okay. And maybe a second comment here is that this is, I think this is the largest contribution to taking our notion of contour and not the notion of MAR partition. When you have MAR partition, you cannot get this exponential bound, you get polynomial bound. And again, when you have this, the proof follows by choosing a suitable large scale that depends on the small scale. So you choose this, you put everything together here, you use this to bound this contour, the size of this region here. You choose L suitably, and you get a bound of this form. So you have size of the contours, scale d minus 1. And just to show how the argument is finished, so we basically concluded that the error is something scale to size of the contour. The number of regions is this exponential term. So as I said before, Dudley entropy bound, you just have to put these two terms and take the square root. So there's a constant here. These are always arbitrary constants, right? And when you do this, you see that you get you have time of size of the contour that is just n. So you have n squared to the square root is just gonna have n, and you're gonna left with sum of, here you have to scale divided by scale d minus 1, so you're gonna have scale d minus 2, and this is only summable for dimensions larger than 3. This is why it does not work for, our approach does not work for 2 dimensions. And well, when you have this bound here on the expected value, we can use just a standard, maybe not a standard, but we just use another lemma to bound the probability of the bad event occurring, and you just see that we have the desired bound. And finally, we go back to the joint space, and here, as you saw before, here we can just do Pile's argument, so we can get a bound of the form exponential on binary constant beta, and this here is bounded by this term here. So this just got smaller than, I don't know, a half for large beta and small variance. At last, let me just comment some future work. For the semi-infinite model, I think the first question that comes to mind is how to treat the critical value, delta equals to 1. So different from paper by Pisacco on the Cassandra et al. In the decaying field, we cannot treat this critical value. Basically, as long as the external field is summable, it's not summable. We cannot. Our definitions to show phase transition, for example, do not hold anymore. So we need a different and actually different approach. But I expect that it should behave in a sense like the external field, so the decaying field, right? So there should be phase transition for small lambda and uniqueness for lambda large. And another question is, consider a long range semi-infinite model, because what we did is not precisely a long-range interaction, right? Because it only interacts vertically to the wall, but it resembles the long-range interaction in a sense. So I think the next step should be put long-range interaction and everything and see what you can do. And for the long-range random field Ising model, again, maybe the standard question is to see if we can actually recuperate the external field with the same critical temperature of the Ising model, as in the paper by Jing, Liu, and Xia. And then the natural question is to expand it on first in one dimension to cover the entire region from 1 to 3/2. And then do it in 2 dimensions. That again should have phase transition for alpha between 2 and 3. And well, here are some references. I used it, and thank you.
Okay, thank you. So we move to directly to the questions phase. I'm not sure about the distance criteria, so I guess I'll start with the people from outside and then your seniority for that.
Yeah.
Should I start with him?
So, it was very impressive. Thank you for your presentation and also for very nice thesis. So you have a strong focus on this long-range stuff, of course. Nevertheless, allow me to ask you something about the short range, about the sting approach. So I have a couple of questions. So to me, it was not completely clear, when do you need that you really have Gaussian variables or just Gaussian tails, Gaussian bounds? I mean, you have various, I mean, the Fischer-Fröhlich-Spencer stuff when you sort of controlling suprema of these energies, no? And then you have also mentioned the Dudley entropy bound. Is that for actually Gaussian processes or processes with Gaussian tails?
No, the thing is, you need, if you're using Tingen's approach, you need to be Gaussian, but I mean,
but why?
They say that you should be expected to be able to erase this Gaussian restriction. Maybe
So
I don't know if I have something like this.
you have the probability distribution, and
Yes.
if it's even, then this flipping argument will work, but you need somehow to control these. Maybe you can go to page 18. Could you maybe go to page 18 when there was this flipping?
Here. No.
Yeah, or exactly the bad event. Exactly.
Yes. So then let me tell you why do you actually need Gaussian? Again, should be able to remove, but you actually need it. But it's basically to prove this lemma here, to prove how the this delta function decays. And this happens because this is basically a consequence of a theorem by Talagran, I actually believe, that shows how to control the decay of functions that are functions of Gaussian that are Lipschitz. So what they actually show is that this delta is a Lipschitz function of age, right? And then you can use this theorem by Talagran to get this bound. Again, and why do I say you have more freedoms? Because as long as you can prove something like this, something like this, like a decay of this sort for this delta function, everything follows as usual. But as they use this theorem that requires H to be Gaussian, then you strictly in the Gaussian.
But what would you expect? I mean, if you don't have Gaussian, exponential tails, of course, then you don't have Talagran theory, etc. And so you get worse estimates and also for these. But do you expect that you would still get something? Maybe one has to dig into probabilistically with the suprema.
I don't think so, because like
maybe.
Because we mean by exponential tail something like this. Now let's say this delta A decays as something like lambda exponential minus lambda. Let's see, over, right? And this should not this should not work, because, well, I mean, yeah, maybe it does, but there's other for here, right? Because this decay is just too it's just too slow. But the idea is okay. Let me give you an intuition on why, for example, you need to use this Dudley entropy bound when you're trying to do. Why don't you just use this bound directly, right? So if you try to do this bound directly, you would have something like this. So here you would have let's say the probability. You want to see the probability of the you're in the plus boundary condition, right? And you want to see the probability of being -1, let's say, right? So for some reason you're trying to do everything at once and you're not considering anything. So here you're just gonna have I don't know. Okay, let's not do the full Paris argument. Let's just do the control on the bad event. So I want to see that the probability of the supremum on delta interior. I'm gonna even do for a short range case, right? You're considering that. So you have this, and you divide it by size of the contour, right? To simplify things, let's look of contours with fixed size. So let's just say n, and here let's just replace this by n, right? Want to see the probability of this being bigger. So what do we do? If you want to just use an union bound, for example, you're just gonna have you just summing over all the contours, right? And you have the probability of one of these things happening. So one of these things happening is something like that. So it's exponential minus lambda square. Here, let me put lambda, right? So we are in the same settings. So lambda square, and you have to divide by the size of the interior, right? So you divide by the size of the interior. Okay. And the thing is, this size of the interior here is something okay, but now I lie to you, right? Because there is this n here, so there's an n square here also. Yes, now we're good. And the thing is, the size of the interior by the isoperimetric inequality is smaller than n 1 plus 1 over d minus 1. Okay, so you have to consider the worst case here, and this is going to be something like, you know, you have an exponential number of contours, and you have
That's too much.
that's too much, right?
Yeah.
So you have exponential, and here you're gonna 2 minus this, so it's actually gonna be 1 minus 1. Oh, there's an n here, right? And 1 minus 1 over d minus 1. See, that's too much. That's why you need this sort of entropy bounds. But the thing is, if you try to replace this by I don't know, an exponential bound, you're not gonna even have t square here. So we're just gonna have something that is strictly negative here. So
Okay.
it's probably not something that's going to work.
Maybe a quick question. So if somebody is just interested in the ground states, because the very first paper on the random field Ising model, nearest neighbor,
Yes.
it was by Imbri, when he also had some complicated, I don't know, coarse graining procedure, but different from the Brigmont-Copiane and different from the Ding. Here you use this joint measure, this Q measure. Does it have any meaningful limit? I mean, the second part, the Gibbs measure, then becomes a Dirac measure on a ground state. Can you? I mean, does the proof become easier? Would you expect? I mean, it's already sort of easy, but shorter than the other proofs. But is it? Do these formulas have meaningful limits when beta goes to infinity?
I don't actually know. When you asked me that, I started thinking if we could do something similar to like what Ingrid did, right? You basically you take the ground state and you ask, I don't know, you want to know the probability of the ground state as 0 being 1. And I don't know how many of these things actually work when you take beta going to infinity. But if you want to do something similar to what Ingrid did, I think there are basically two scenarios. So, like for example, we want to do something like this, right? You want to do something like this. You take you want to know the probability of you put plus and you take the ground state and you want to know the probability of this being +1, right? So I think there are basically two scenarios. Either you can write these events, I don't know how, but in a way similar to our bad event.
So, sorry, P is for you. Yes. Okay.
Yes.
Yes. P is the P, and the ground state is almost truly unique in finite volume. Okay.
Yes. So let me find here. Let me go Yes, okay, I think here's good. Either you can write this event as something, I don't know, similar to that thing here, to our bad event, and then all our methods should be applied like just like the same. If you can write this event as something similar to the one, then everything should be easy. Otherwise, I think you would have to look much closely to Ingrid's paper, and you had to do something more similar to what he did, and I think it would work because again, yeah, he does some sort of coarse graining arguments on the contours because he has a problem with contours inside contours, right? And he goes approximating contours that are near the boundary, something like that. And I think you should be able to replicate mainly the key ideas of what we do here in his scenario. Because the advantage of using our contours is that, again, he has a problem with contours inside contours, right? But the advantage of using these disconnect contours is that you don't have freedom to put any contours you want inside contours. Because, for example, if you are in usual Poisson argument, you can have anything right inside your contour because any configuration is a valid configuration. But when you have our contours, these things do not happen. So, for example, if you have a contour like this, right? If this is a contour, let's say gamma 1, we cannot have a contour inside this contour that is something like this, for example. You see? You cannot have this kind of stuff. You cannot have, for example, this thing here that is can be small but is close to the original contour. You cannot have this thing. Okay, so we have actually less bad cases. Again, his argument step by step would not be the same because I remember I took a look at this paper sometimes, and he clearly uses connectivity. He basically can control the ratio of the diameter in the size of the contour, which is not the case here anymore. But yes, but again, we had an advantage that he doesn't have, so should be
Okay, thank you.
Thank you, Christophe. So for the record, that was Christophe Kursk asking, so we now move to Pierre Picot.
Okay, thank you very much for your just perfect.
no, thank you.
I say it. Okay. Okay. Just I want to say something about the question of Christophe. I think that the real hypothesis you have to put on a magnetic field is that the random variable should be sub-Gaussian.
Yes.
That's the real hypothesis in physics. From a physical point of view, this is sub-Gaussian. That includes the Gaussian and the plus or minus 1 with probability 1/2. These are all hypotheses. Natural hypotheses. Okay.
Yes.
So first, I'm sure that this kind of argument where you use you have a function that is Lipschitz with respect to the variable will work for sub-Gaussian.
Yes.
You have just to even you can try to enter in the double method for finding this and working. Certainly, you will get the same thing because a priori Talagrange result. There are also Talagrange result with respect to the plus or minus 1 Bernoulli random variable. There is also exists a theorem like this. Okay, so a priori the real hypothesis is to be sub-Gaussian.
Yes.
Okay, so now at the end I would like to speak at the end of the open problem you mentioned.
Oh, okay.
Okay, so I will answer to what is my opinion about the last the last one and the previous to the last. Okay.
Okay.
Certainly you can do it. We try to do it with Jorge Lipin. Okay, but we try an afternoon, and after we say, oh, it's too complicated. But you can try. You have to be careful because there is an argument that comes from the Ulinsky method for computing, where you write martingale difference sequences for something. In this article we did with answer Orlandi. There is a kind of argument when you start. You have to find the difference between a random variable and its expectation, okay? And you write a kind of telescopic sum, and you treat each term of the telescopic sum in some sense. Okay, we did that, and the computation are complicated. I agree with you. This is very complicated. You have to make a lot of computation, and at the end, happily, you get the result. But I'm sure that it works in this region also. I mean, but I'm not sure that the same method we used could be applied. It was important that at some moment we are able to treat to make the comparison with a lower bound that was in the whole paper in one dimension is with respect to the triangles.
Mm-hmm.
Okay, there is something that to say that the excess of energy is larger than something that depends on the triangle. This is not true in general. What we prove with Jorge leading that this is not true. You have to make the decomposition with respect to contours. I mean, the Hamiltonian is additive, okay, or quasi-additive with respect to the composition in contours, not with respect to the triangles. That is what we discovered. So perhaps you can do, working a lot, not too much, but more than one afternoon, you can succeed to solve the last problem. Okay. I just mentioned that we work an afternoon, and after I say, oh no, okay, but try to work on this. I'm sure that it works. Also, the last question, can we extend one argument to d equal 2? I say, yes, you should do that. Because certainly it is true. There is no reason to have a phase transition in d equal 1, and you have to jump to t equal 3. It is not possible.
Yes.
Life is not like this. I'm sorry to tell you, it is not like this. Okay.
Yes.
So it is certainly true that you have, but the fact that you have d equal 2 is just as a moment of a technical computation.
Yeah.
So I'm sure that if you concentrate on this part, you will find something. There is no reason for this kind of model.
Okay, let me maybe make a little comment on that. Again, let me go back here to this bed event here. So again, we want to control something like this, right?
Yes, yes.
And it's actually there's a paper I mentioned this before by Jing and Matthew Wirtz that they show that an event like this cannot be controlled in 2 dimensions. They show that basically this probability diverges with the size of the box. But there is
no, it's not the probability that diverge.
yeah, but no, the expected value of this thing.
Yeah.
But there are there are ways around it. Basically.
No, but also there's a question that after you at some moment you write an estimate for the expected value of the supremum, okay? Because you want to use Dudley arguments, okay? But you can try also instead of, because doing that a priori you will use a Markov inequality at some moment. You can try to do better. Instead,
yes.
So this part you have freedom to work a little more. Not using the expectation of the supremum, but directly the probability of the supremum.
Oh, okay.
Yeah. Not passing through the other one, passing through the Markov inequality, because you can lose something there.
Mm. Yeah, I remember I actually read the paper on 1 dimension, your paper, for the random field, and I see that you don't take the expectation, right? You do it each event.
No.
Yes.
All the problem in the statistical mechanic of disordered system is that you always have to study the probability the supremum of something is like. This is the main difficulty. And using the subadditivity that you mentioned, it could be bad because just you are counting too much events, okay? Mm-hmm. And instead of making a partition where you make all the possible of your event, if you, the idea of I don't know how to call that. there is a way to organize
Yes.
a union, make a partition of the union taking care of, and you can do better. Usually, we have to be careful when we do that. Okay.
Yeah.
That's all I want.
Cool. Anything?
Thank you, Pierre. Now, please, Leandro.
Well, thank you very much. Thank you, Rodrigo, for inviting me for this. It was really pleasant to read this thesis. It was nice also to be part of your qualification exam. I remember seeing the results that you first proposed and like you managing to go after them. So it's really cool. And also thank you for writing this thesis in a way that we go through the classical results before jumping into long range because it makes life much easier to read.
Yeah.
So yeah, I have a few questions. I remember that back on your qualification, you're kind of thinking of looking at correlations for the semi-infinite Ising model, like via random currents.
Yes, we are. Actually, that's a very good story because we're trying to find a new way to prove uniqueness using this the decay of correlation in some sense, using the random current representation. And turns out what happens is that I did it. I proved the uniqueness using random current. And then I started proving a lot of stuff that was known to be false.
Oh.
and then and then and then I found a mistake in the argument basically because we want to compare the plus and the minus boundary condition, right?
Mm-hmm.
And if you try to write this as using the random current representation, you end up with weights that can be negative.
Mm-hmm.
And when this happens, like there's no hope anymore. So to save it, so everything went to the trash basically.
Okay. Okay.
Yeah.
But right, no, that's fair enough. Because I remember that you went because there's some recent results using 5.4 via random current kind of argument.
Yes.
I was going to ask if this.
Yeah. No, you can. I think like there is one important thing is that sometimes you want to compare the plus boundary condition with the free boundary condition, right?
Mm-hmm.
And when you do that, you can do. I mean, that's why you can use random current because then no weight would be negative.
Mm-hmm.
But for our case, so to be fair, we can prove, we can show that I don't know the plus boundary condition matches the free boundary condition.
Ah, okay.
Mm-hmm. But I don't think this is enough to show. I don't know if this is enough to show phase transition because the thing is you do not have symmetry anymore.
Mm-hmm.
So you see, because even in the minus state, your state can be positive now, because you have an external field that is positive. So you don't have spin flip symmetry, so it's not enough to compare the plus and the minus.
Okay. Yes. Oh, nice. Well, good to know. And then, like what I wanted to ask about the random current kind of approach. Sorry, the random field part was so. Yes, if you could go back to page 16, I think. Yes. Yeah, so going in a different direction to like generalization of what kind of fields can be there. Mm-hmm. If you had a Gaussian field but correlated, you could still use the same kind of approach in principle, like spinning the flips. But of course, when you try to do this quotient here, you're gonna have to pay a price. Start with finite range, for instance. Say you have IID Gaussian random variables in each site, and then you take an average of like the nearest neighbor, so it's really independent as soon as you get like to distance 2. Or you can go further than that, put a kernel that is truly long range, but starting, yeah, so do you, because Dudley's bound and all of those arguments should work in principle, but you have to control different types of bad events now, right? Because you have to control how much damage flipping the field would be, like saying in nearest neighbors Ising model. You think there is?
Yeah, no, that's a very good question. So yeah, that's a very good question. But let's think first on like you said, the average on fixed radius, right? So as you see, this notion of contours we presented, we use this notion of incorrect points that you only look at the first neighbor, right? You look at the neighbors if you see that's incorrect. But you can actually fix a range for your incorrect points, right? So you can fix a range for, let's say, everybody in some distance is of the same size. I think using contours like this, maybe, yeah, let's try not to look at the external field to choose the contour. But if you choose contours like this, everything should work equally, and this change on the external field, you should be able to get around it.
Okay.
Because your contour is actually writing down everything that is near, in a sense. So I think hopefully you can deal with this sort of dependency.
Okay, cool. That's interesting to know. Yeah. Yeah, I think that was it. Thank you very much.
Thank you.
You go first. Okay. I have only minor points. Well, first of all, congratulations on a very nice project and great results. So my first point, I guess I'll only make two minor points. So the first one is about I believe I have a version of the text which is probably not the most up to date. I realized that, I guess, looking at the talks, previous talks, and now your talk. So one important thing, crucial thing in your results, as you pointed out, and previous people talking about that also did, is different notion of contours, so in the version that I have, at some point you start by referring to previous kinds of contours, like the ones by Rodrigo and co-authors previously, and then you move to the next, to the one that you use, and then you mentioned that you're going to work with the finer version of that one, and at some point you also introduce these ones that have an R, right? So these are the ones that you actually work with, and then you get the results for the finer ones by just comparison to those. Is that it?
Yes, like throughout, maybe not in the version you had. I still use it. I always use these new contours, these MA partitions. Well, okay. The difference basically is this. Let me go back there. Here. So the difference is this, like the partition, it only depends on A and M, but we still have the R quantity, but it comes in the construction.
Right.
But essentially, throughout the paper, we are always using these contours here, never the MAR partitions. So it's always like this. In the version you got, I think all of you got, we still have some estimates that were made using not the previous contours, but the estimations were the same, right? Because well, the estimations are the same, but we are using these contours. I think in the most recent version, we basically got rid of every estimation that is the same for the two contours. So we have estimations that only works for these contours. And the advantage are two. I think the most important for future work is this here. I think this here is the most important for future work, because we actually change this from a polynomial to exponential. This is very important. I think, yeah, this is the key difference. And for this application on the random field, the most important consequence is actually on this bound here. You see? Because this is the same bound we got for the short range case. You have this C here that is a constant that may be bigger than 1, but it's not relevant. This is only achievable using this new notion of contour. If you use the old one, you get a bound like this. You're going to have this BL, right? This BL of C0n, which is the number of admissible regions. And you're going to have something like exponential. And you're going to have that term, so L to a constant n to R L d minus 1. And you're going to have an extra term here of the sort, again, L to a constant n to R L d minus 1 minus some error. Okay? In our construction, you get something like this also. But the thing is, you get something like this. This part here comes from the approximation of your choice of admissible cubes. So this choice contributes as this factor. And this extra factor comes from the choice of contours. Basically, this comes from the entropy of our contours. So when you try to do using the MAR partition, you get something that is not d minus 2, but you still have an error. But when you use the new contours, you can put anything here. You can change this d minus 1 for anything. In particular, I don't know, you can put 2 here. So you see? So the restriction to 3 dimensions comes from the approximation, do not come from the choice of the contours. So you see that's actually why I think these contours are, maybe optimal is a strong word, but yes.
Right. Yeah. I was thinking more of because you're talking now about the old kinds of contours that were used in Lucas' thesis,
Yes.
and you need the new ones. No, that part I guess I got. I was just a bit confused in the presentation that you start using a MA delta contour, and then
Yes.
and then you had also the finest ones, and then you have these ones with the R, not the MAR, this gamma R.
Yes.
And then I think I understood that you work with the gamma R, but once you get to the gamma R, the finest ones are, you get things for the finest ones just by comparison.
Yeah.
Is that the case?
Yeah, I mean, again, maybe a little, another piece of history. In the first version of this paper, I don't think I even written this MA definition of partition. I just defined the construction, because it's the construction gives you everything. It gives you the distance. It gives you the basically the number of cubes in each component. That's the key property. So the construction gives you everything, right? So I didn't even written this definition of MA partition or anything like that. I was just using the construction. So so yes, the construction is the important part. I just put this definition there because I think it's easier to see what you are actually doing, right? You just partitioning in a way that works for you, and the finest partition satisfies something.
Okay, good. Thank you. Another point, which is really minor, but I didn't see it in the thesis, but I think it should be there somewhere. It's just a minor thing, but it's important in the sense that when you state your theorem, you say that something happens almost surely for P almost every realization of the field, and then in the proof you prove things with large probability, right? So if a probability is close to 1 as soon as you take So I mean, there's something there to be said about how do you go from that to the. I mean, it's a minor thing, right? It's just
No,
because
it's
things
a good
are.
thing. It's a good thing to add. Yeah, you need
You just have to use
you
some
need an
0 or
extra
1 law or
argument.
something. Sorry.
You need an extra argument. Yes, you are right. We showed that the probability is large, right?
Right.
But you need and then you need an ergodicity argument because you need
Yeah,
to
yeah,
show
that's
that
right.
it
That's
happens
right. Yeah, yeah.
with probability 1 or 0.
Yeah,
Then you
yeah,
need
but
some
yeah,
extra
yeah. So,
step there.
but related to that, I mean, if you took I mean, I'm not suggesting you do that, but if you took your field not translation invariant, but independent, but with some bounded from above and below, I'm pretty sure your arguments would work for those two, right? And
Yeah.
and then but then you would lose the translation invariant, and perhaps you wouldn't be able to use this 0 or 1 law. I'm not sure, but I mean, I'm just pointing that this is a kind of thing that at some point we should say. I mean, it's a two-line point, but I mean about the going from your results to the almost sure.
Yeah, it's almost
Statement, but I mean, it's a minor thing. But in any case, I guess it should be there because you stated it as almost sure.
Yeah.
Okay. So my last thing is perhaps a wild conjecture, and not conjecture, speculation about the 1 and 2 dimensions. I mean, so in the model with no field and 1 dimension, the long range, you have these. This sort of Thouless effect, the second order phase transition. I mean, do you expect to see any of these things in these models? I guess the dimension should be 1 or 2. I don't know.
Yeah, dimension
Perhaps
1
there's
or
nothing like that.
2. There is, I think there is one paper by Abel Klein that he studies the decay of correlation in this long-range model. It's actually a very not as well known as it should be, but this is the only result I know on decay of correlation for the long-range model. But if I'm not, but if you want to see, if you want to know, there is phase transition for this. Yes. I mean, I wouldn't. I would say yes, right? Because you expect the same thing to behave as for the short range. But I have yes. I wouldn't bet on it. It should happen, but I think we are not too close to approve.
Okay, thank you.
Okay. About the almost sure, you know, João, I told you.
Yeah.
We forgot because we said several times to add, and some moment we forgot.
Yes.
Okay, so okay, I don't will comment about the presentation because we saw before, and I just will make the, let's say, a historical remark about the trajectory of João. So for I don't know if you know, but we have 3 options to study here at IME. You can do more or less 2 during the day, right, in the morning and afternoon, and you have we can go at night also, even for people that work and so on. So and here in the institute, they have we have a problem of the amount of teaching. So we have the 4 departments: statistics, computer science, and pure and applied mathematics. So and then the pure mathematics is completely full. They have problems, a lot of teaching, and I am from the applied department. So, and sometimes people from applied math department, they teach courses for the PUR. So it's one of these occasions. Then I will help. I was there helping the colleagues from the PUR department, and I go to teach at night. So okay, João was there, and I think it's linear algebra 1,
Yes.
a very advanced course. And so okay, João was there, and okay, and you know, and this sometimes people think that these students that go to the night classes, they are not so clever. This is very not good thinking, I guess. And then I was there teaching linear algebra, and okay, João, okay, he found a mistake in my exam, and things like that. And I had a grant, and for students. So I asked João, okay, João, why are you studying night? Do you work or something like that? No, I don't know. So okay, jump to the day. So okay, so I invited João. Maybe it was bad luck for you or luck, I don't know. And so Joe came for our group, and okay, he switched to the day, and he started to work with us. So actually, he worked with trees and the models with us. Maybe he was following your, maybe the best person to follow your talk. It was he did a final project in the undergraduate studies, reading the Georg's book. So he knows a lot about the Ising model on trees, and after he started to the we call here the doutorado direto. It means that because in general in Brazil they do the undergraduates, master, and after PhD. So he jumped directly to the PhD level. So okay, so since Pierre Pico already notes it, is we have this FAPESP agency that we have very lucky that we have this, and so we managed to get a scholarship for João. And so now I will say something in words that I think is important, mainly for the students, because now we are in the week. It seems everybody very successful, a lot of good results, but this is kind of 6 years of work, and we have a very bad luck in several times. It was very difficult. We have pandemic. We have, I mean, this is a very good moment, but it was during several years. It was really not clear that we will achieve what we have today. So okay. So since we work as a group, when someone see opportunity, we share. So there is a student now. He is in New Zealand. They call Rafael Pereira. So Rafael Pereira saw an advertisement about a master class in Geneva. So where is Velenik there and these people? So Rafael Pereira sent us the opportunity, and then the more or less the only student that was available and in exactly good conditions to go, it was João. So we applied to Geneva University, and he got the grant, and he passed the 10 months with Velenik in Geneva. It was now you think, well, very lucky. No, pandemic. So I don't know, 2 weeks, I don't know. So João was there, and I don't know, 1 month, maybe less than this pandemic. So it so it was very challenging. This is I have to emphasize. Now we have a very strong, very good result, but it was we have good luck and after bad luck. So João was there, and he worked a little bit in the semi-infinite problem with Ivan, and after he came, and we continue here. And what happened that while all this process, so João was in Switzerland, I was in Poland. We are in different countries many years apart. So that was very important to have the group. So João came, and I went to Poland, but he was Lucas when João came back to Brazil. So Lucas just got this idea to the contours, the first version. And so we did this first paper with Endo, Handa, and Lucas. And so we have the first version of the contours. So, okay. So, and then Lucas found this paper of Yan Ding. And João was not so happy with the same infinite project. So Lucas, okay, why not? So, okay, let's go there. And during this, I don't know, past 2 or 3 years, João was working very hard in this random field project. So he read this Fisher-Fröhlich paper. It is not easy at all. He completed the proofs. The proofs are correct, but they very difficult to read. I mean, these papers are very difficult to read. So in the middle of the year we have a conference where Lucas finished his PhD, and we were running to João also to present his results. But in the last proposition, of course, a mistake. So we more or less was very sad. I mean, so many work. I mean, we in the last result. And then I said, okay, João, let's do the same as Lucas. Okay, go to D+1, which is more or less sure that we will get the result. It is for now. After 3 days, you more or less see that D+1 is more or less some kind of let's say bigger than +1 is a safe place for long range results. So okay, João, write D+1, did the life, and let's go. And actually, João did this, and he presented in the conference in the middle of the year. And it was Abel Klein here, a lot of people, we discussed, and okay, that's the life, let's finish the PhD. But João never gave up, and he got this idea of the, I don't know, maybe the big L, exactly this. Now, okay, so this big L, and also, as you mentioned, he has this more clean version of the contours of Lucas. The contribution, not only the big L, but also, maybe go to the definition of contours, because this is, you can easily state what is the contours just using, because if you remember, because Lucas is okay, he was 3 years working to find the right definition for the contours. And if you saw our first paper, you see the diameter. And then, again, since FAPESP, we got these results, and we tried to present here in Brazil. And I wrote to people, okay, we have very good results here. Can you invite us? And I was not so lucky for here in Brazil, surprisingly. And I wrote to Yan Ding in Peking. And we wrote to them, and I said, okay, I have very good students, we have results, we use your paper, can we present in your seminar? And he said yes. So I got the yes in Peking and no in Brazil. And since we have FAPESP money, so we send a mission of Brazilian students to Peking, and then there João and Lucas present to Yan Ding the results there. It was very nice. They actually, João already has a position there. He has a job, and very good job, basically. And then it was after this. Then I think Ding say some things to you. If you use the diameter, you can have very sparse contours, right? Instead, if you use volume, maybe you can avoid these very sparse objects. So that's why one of maybe the seeds in this João mind, not really, let's say, a specific comment, but it was enough to João to finish the project. So that's just, I think, is important remarks, because now it seems that everybody is very super group and so on, but it took 6 years of everybody here. And another thing about the personality of João, it's a very good, let's say, colleague that to have in your group. So he's very stable. He is friendly with everybody. and it's very good. He's a very good collaborator and a very stable person for the other students mainly also. So I think this is important also because sometimes you have very strong students, but they are not so friendly with the colleagues, and this is another thing I think important to add. So it's the thesis is very good, and I'm very proud of the students, and including João, and maybe this is good to highlight this is one of the main contributions, and also then to manage to end the proof. I by myself I gave up in some moment, but João he continued. So congratulations. So I have to say this.
Thank you. So now we move to the to the not so nice part of the defense. So we have to ask the everybody out. I'm sorry.